today. We are starting really with the atom here, and that's pretty much what we talked about. Excuse me. What we talked about last time. We talked about really the structure of the atom, some major experiments that led to sort of the understanding of the modern structure, obviously, of the atom. So we started with sort of early experiments that really dealt with electrons, and that was Thomson using the CRT tube, the cathode ray tube, to really investigate the nature of sort of electrons. And he was able to figure out the charge to mass of an electron. And as we talked about last time, that was sort of followed up by Millikan and his oil drop experiment, where he was able to really determine sort of the charge of an electron. Again, using both of those pieces of information, as we talked about last time, the mass of an electron was able to be basically determined. And our mass of our electron was 9.09 times 10 to the minus 28 grams. At that point, and with sort of the experiments that were going on, again, as we talked about, there was sort of a belief that obviously the atom was neutral, and these negatively charged electrons were sort of discovered through these experiments. So the early model of the atom was that plum pudding model that was done by Thomson, and it was the idea that all the positive charge was pretty much spread out over the sphere of the atom. Embedded inside were these electrons, and that the most of the mass of the atom was the electrons. And that was sort of the accepted version of the atom until, again, another major sort of experiment occurred, and that was Rutherford's experiment. Rutherford's experiment basically shot alpha particles, which are radioactive positive particles, basically helium type of nucleuses. And he shot out pieces of metal, gold metal, and other metals as well. And what they anticipated to happen based on sort of the plum pudding model was that most of the sort of alpha particles, which are sort of heavy, moving really fast, positively charged particles, would show some deflection as they kind of went through that whole kind of positive charged spread out over the atom. And they were a little bit surprised based on their findings that what they really did find was most of them went through undeflected, which, as we talked about, basically meant that they pretty much ran into nothing. They pretty much hit empty space. Every so often, what we saw there was every so often what they saw was a alpha particle would be basically scattered at large distances. And so what they basically found was that it had to hit something that was very, very densely positive. So that sort of threw a wrench into the early model of the atom, and they sort of disbanded that, if you will, and went with sort of the current, obviously modern version of the atom, where basically the atom is mostly empty space. It contains a central sort of core, positively charged nucleus, which was later found to contain the protons, which are positively charged, and also in 1930s found to contain obviously neutrons, which have no charge. In that sort of empty space, we have our electrons basically traveling about the nucleus as sort of a random pattern, as we'll continue to talk about. The other major difference between the two models was in the modern version here. Obviously, most of the mass of the atom is made up of the nucleus, and that does make sense based on sort of the numbers that we talked about as we went through the different experiments. What we saw was a neutron is actually the heaviest of all three of those subatomic particles: proton, electrons, and neutrons. Neutrons being the heaviest, just slightly edging out protons, and then our electrons are much, much lighter. They're about 1,800 or so times lighter than a proton and a neutron. I think that's about where we left off. Any questions on any of that stuff that we talked about last time? And again, a reminder, if you do have questions, feel free to ask them. Again, you can ask them through your microphone if you like, or again, you can send it in a chat message. So I think this is about where we left off, if I'm not mistaken. So let us continue on here. So the nice thing about sort of, I guess, atoms and so forth are the idea that pretty much most of the chemistry that we deal with in sort of general chemistry, not nuclear chemistry, which again, you do get into a little bit of nuclear chemistry in 200B if you're going to continue on to take it. But here in sort of general chemistry, pretty much everything is pretty much electron based, if you will. It's about bonds, it's about bonds being broken, and that's all really about the electrons. So under normal sort of circumstances, really the protons, the neutrons, they really don't participate in any type of sort of chemical reaction. It's really those electrons that are on the outside of the atom that sort of participate. And it does make sense if you think about sort of the atom, you got the electrons flying around on the outside, in the center is sort of the nucleus where protons and neutrons are. So, when two atoms come together, it's obviously going to be those electrons that really do come together first and sort of are going to sort of interact with each other as well. So let's talk about some other important aspects of an atom, and that's the atomic number, the mass number, and what isotopes are. So we'll start with sort of isotopes. Isotopes are really the same element, but they do have different masses and they do have different numbers of neutrons. And it's really the neutrons that make the difference there in terms of the mass. And if you remember, that was one of the sort of things that the finding of isotopes and the existence of isotopes is one of the things that basically made part of Dalton's atomic theory sort of incorrect. If you remember, he said that pretty much all the atoms of the same element are identical, and the existence of isotopes basically disproves that. Again, you have the same element, but they have different masses, different numbers of neutrons, which means that those atoms are not identical to each other. But one thing that is very similar in terms of isotopes are pretty much they do share similar chemical properties. And that's due to really the number of electrons that are present. So sometimes isotopes, for example, of different elements, some may be radioactive, some may be sort of non-radioactive, if you will. But in terms of how they sort of interact, they do interact sort of the same way because they're really the same element. And in normal situations, it's just those electrons that are sort of involved. And the major difference is the neutrons, and it won't have a very big effect on the reactions that are occurring. So here again is two isotopes of sodium, and that is sodium 11, sodium 23, and sodium 24. They both have basically 11 protons. So that part of it, what's in the nucleus there, in terms of protons are the same, but it does have different numbers of neutrons, and they do have some different properties depending on them. So again, they're not identical to each other. They are slightly different. And again, different mass made up of those different neutrons. So let's talk about one important number, which is the atomic number. And the atomic number, which is sometimes abbreviated as a Z, is the number of protons that we find in the nucleus of an atom of an element. Now, if an atom is neutral, as we talked about, pretty much there's just protons, electrons, and neutrons there, which means if they are neutral, the number of protons, which are positively charged, should be balanced out by the number of electrons that are negatively charged. And what that means is the atomic number will also tell you in a neutral atom the number of electrons that are present. But it is an important note that if you're asked a question of what does the atomic number actually mean, the definition is only the number of protons. So it is only the number of protons. A side note to that is if you're talking about something that does not have a charge, then again, it will also tell you the electrons, but the actual definition is actually just the protons. Now, when we look at the periodic table, for example, we can find the atomic number on the periodic table. So for example, if we look at our good friend there, hydrogen, 1.008 and 1, it is typically the number that is above the symbol there on the periodic table. You look at copper, which is 29, is that one. And again, you look at something like, say, Cl. Is this number. So you definitely can find the atomic number there on the periodic table. And if you have a periodic table near you, or you're looking at one, or when you do look at one thing that you will see when you do look at a periodic table, for example, is if you look at the top number, there is no number that repeats. And that means that the atomic number, which tells you the number of protons, is the important thing in terms of determining the identity of a particular element, or what element that you are talking about. So it's actually the protons that determine basically the elements that you are talking about. And that means that the number of protons determine the element. And that's a really important thing, because basically if you have the atomic number, or the number of protons, which are essentially the same thing, you can definitely use the periodic table to determine, again, who you are talking about, what element you're talking about. So for example, if we look on the periodic table for nitrogen, nitrogen is number 7 on the periodic table. That means that if we have a neutral nitrogen atom there, so if we had a neutral nitrogen atom, it would have 7 protons, which are positively charged, and to balance them out, it would also have 7 electrons, which are negatively charged, and gives us an overall charge of 0 in this particular case. So the atomic number found on the periodic table definition is the number of protons. The number of protons in an atom will tell you what element you have. Again, you will never see a nitrogen atom have 8 protons, because somebody that has 8 protons is oxygen and not nitrogen. So protons really important in terms of the identity of what you are talking about. Now, the mass number is another important number, and the mass number is the number of protons plus the number of neutrons that you find in an atom. The mass number, which is abbreviated A, basically, again, tells you both of those things. So the mass number and the atomic number are important sort of two numbers, because if you look at both of those things, so we have our mass number, which is the number of protons plus the number of neutrons, and we have our atomic number, which is the number of protons. If you essentially subtract those two, number of protons cancel, and that tells you the number of neutrons that are present. So we could actually use the mass number and we could use the atomic number together, and that will allow us to determine how many neutrons there are in a particular atom of an element. Now, we talked about a second ago that you could go to the periodic table there and find the top number, which is our atomic number. Now, can you find the mass number here on the periodic table? And the answer is no. You cannot find the mass number on the periodic table. This number that I just boxed is not the mass number. It is what is known as the atomic mass. So it is different. So you cannot find the mass number on the periodic table, even though most people will kind of use that number, but it is incorrect. It is not the correct number for the mass number. And the reason for that is when you calculate all those things, when you calculate how many protons an atom has, how many electrons, how many neutrons, when you calculate the atomic number and the mass number, all those things need to be positive whole numbers. And when you look at the periodic table, pretty much everybody on the bottom there which is the atomic mass, are not whole numbers. So that's a good way to remember it. It does need to be a whole number. That definitely is not a whole number when you look on the periodic table. And again, that is not the mass number. That is the atomic mass, and you should not use it for it. So if you're asked to calculate the mass number, you're asked to calculate how many neutrons and so forth, you definitely will be given enough information to allow you to sort of calculate those things. Any questions on that there? Now, isotopes, as we talked about, are, again, the same element, but it does have the different number of neutrons, which means it does have a different mass because of the number of neutrons are different. And for example, if we look at hydrogen, hydrogen has 1 proton and no neutrons. Deuterium, which is heavy hydrogen, sometimes referred to, 1 proton and 1 neutron. Tritium is 1 proton and 2 neutrons. Pretty much every single element will have protons, electrons, and neutrons, except for, as you see here, our hydrogen only has 1 proton and 1 electron and no neutrons. But everybody else besides hydrogen will have neutrons. It's, you know, kind of the only exception that we have in terms of that. Now, when we do write isotopes and so forth, we sometimes will display it as we see down here, where we will use the chemical symbol, and up on top left, we will put the mass number. Up on the atomic, up on the bottom left, I guess down on the bottom left, we would put the atomic number. So if we were going to write the 3 sort of symbols for our isotopes of hydrogen, we would start with hydrogen. It would have 1 proton. If you weren't sure what the symbol would be, you would go to the periodic table and find number 1, and it would say hydrogen, or H. And because it has 1 proton, that is the atomic number, which would go on the bottom. The mass number, in this case, would be the number of protons, which is 1, plus the number of neutrons, which is 0. And that gives you 1 there for our mass number, which would go on top. Now, when we come over here to deuterium, you may go, I don't recognize that name. I'm not sure what that is. But what you can do is obviously look at the number of protons. And when you look at the number of protons, it does still say 1, which means if you go to the periodic table, you will see the same symbol for number 1, which is hydrogen. Also has a atomic number 1. Mass number for this guy, though, is 1 proton plus 1 neutron gives us 2 for the mass number, which would go up on top. And lastly, again, tritium, which is, again, the radioactive version of hydrogen. It doesn't sound like it's hydrogen, but has 1 proton, which means, again, it is hydrogen. And our mass number here would be 1 plus 2, which is 3. And these would be the 3 symbols for the 3 isotopes of hydrogen. Even though they have different names, they're all basically the exact same element. They're pretty much all hydrogen. The major difference is up here in our mass number, which means we have different numbers of neutrons. And by the way, typically we take the top number minus the bottom number gives us our neutrons. So if we did that, 1 minus 1 is 0 for our neutrons. Top number 2 minus 1 is 1 here. Top number minus bottom number is 2 for our neutrons. So top number minus bottom number is a way that you can sort of figure out the number of neutrons if you're given sort of the symbol in this arrangement. This is a very common way that you write sort of these symbols. Any questions on that? Another way that you sometimes will see symbols written is, say, like CU-64. And you may be wondering, you know, sort of what does that number sort of represent? Now, that number represents, if you're not sure, if you go to the periodic table like we talked about a second ago and look at copper, again, we will see copper is 29 up there, which is the atomic number. So clearly this number is not the atomic number. That number is the mass number. And obviously, if we write the symbol like we were just doing here, it would be 64 up on top and 29 on the bottom. So again, this is a common shorthand as well for isotopes, that they're sometimes written element dash mass number, basically. Any questions on that there? Okay, let's see here. Why don't you take a couple minutes here, and for each of these, let's determine the number of protons, electrons, and neutrons. And so take a couple minutes, and then we will talk about it. What you're doing. So again, remember that our top number here is our mass number. Our bottom number is our atomic number. So right off the bat, we know that the number of protons in this case is equal to 27, which is our atomic number. Now, we also know that hopefully that this guy is neutral. Again, if it did have a charge, it would be written there. So we do not see anything written there. So we obviously can safely assume that it is neutral and has no charge. And that means that in this case, because we have 27 protons, which are positively charged, in order to balance that out, we do need 27 negatively charged electrons. 27 positives, 27 negatives gives us 0 overall charge in terms of this atom. Now, for our number of neutrons, it is the mass number, which is our top number, minus the atomic number, which is our bottom number. And that's going to be 60 minus 27 and perhaps a 33. Any questions on that one there? Taking the sort of same approach here, our Cl as an atomic number 17, again, means that it does have, in terms of protons, 17 protons. Again, nothing written there, which means it should be neutral. That means we should have a matching number of negatively charged electrons. And lastly, we're going to take our mass number minus our atomic number here to get our neutrons. And in this particular case, that's going to be 37 minus 17. And it looks like we end up with 20 in this case. And for our last one, which is uranium here, again, we see the atomic number given to us. And again, by the way, if it was not given to us, we simply would need to go to the periodic table and find uranium and the atomic number that we see above it. And we see in both cases, it is 92. Again, no charge there means that our electrons should match it. And our neutrons, again, taking our mass number, which is 238, minus our atomic number, which is 92. And that gives you a lot. Let's go with maybe like 146, give or take, I suppose. Any questions on any of those there? Okay. Then let's take a look at some more here. Hopefully they agree. That's good. All right, let's see here. So why don't you do the next example that you have? We want to write the symbol with the mass number and atomic number for krypton that has 48 neutrons. I think the other one you have is nitrogen. With 6 neutrons. And the last one is for iron that has a mass number of 56. How many protons, electrons, and neutrons does it have? And also write the symbol. So for all three of them, write the symbol with the mass number and atomic number. And for the last one, determine the protons, electrons, and neutrons. So see what you come up with here. 48 neutrons, but from the periodic table, we could also see that when we look at it up there on top is the number 36. So that again is the atomic number, which tells us it should go here on the bottom left. And that also tells us that that is the number of protons that it has, which would be 36 protons and 48 neutrons will give us our mass number of 84 in this case, which would go right there. Any questions on that particular one there? Now, nitrogen, again, if you weren't sure of the symbol, you could go to the periodic table, hopefully, and find it, which is N for nitrogen. The other important piece of information that you get off that periodic table is that the atomic number is 7. Again, the atomic number going on the bottom left there. The other importance of the atomic number is that is the number of protons that it has, which is 7. Adding that to our number of neutrons, which was given to us, which is 6, that gives us a mass number of 13 in this case, which would go up there on top. And lastly here, iron with a mass number of 56. How many protons, electrons, and neutrons? So again, going to our periodic table, symbol for iron is Fe. They actually gave us the mass number, which goes up on top, which is 56. From the periodic table, we can see the atomic number is 26, and that would give us our correct symbol in this case. Oops. Now, we also want to know protons, electrons, and neutrons. So here, our number of protons would be 26 to match the atomic number. Again, it is neutral, so our number of electrons will also match that. Again, if you add those together, no charge, basically. Number of neutrons would be our mass number minus our atomic number, which looks like in this case a 30 would do that. Any questions on any of those there? Questions on how to do protons, electrons, neutrons, mass number, atomic number. Again, most of the time, super common mistake is the using the atomic masses for the mass number. So again, remember not to do that. Now, we've talked about things here that are neutral, but what happens if we actually do have something that has a charge? So if we do have something that has a charge, those things are what are referred to as being ions. So ions are things that are charged. And there's really two types of ions that we come across. One is a cation, which is a positively charged ion. And one is an anion, which is a negatively charged ion. So what happens if something does have a charge here? What changes in terms of what we're dealing with in terms of protons, electrons, and neutrons? So for example, let's take our nitrogen here, and we'll do the exact same sort of mass number and atomic number and all that good stuff, but let's give it a -3 charge. So when we kind of go through this guy now, it does have a -3 charge. It still has, though, for its atomic number, 7, which means it still has, in terms of protons, 7 protons, which are positively charged. But in this particular case, it does have a -3 charge, which means in this case, the number of electrons is not going to be 7, but it is actually going to be 10. You take 7 positive things plus 10 negative things, that leaves you a -3 left over. You got 3 extra electrons, basically. And that is basically where, again, the charge comes from. And in this case, obviously, the number of neutrons would be the same, 13 minus 7, which would be 6. So what we see here is when something becomes negatively charged, it actually will gain electrons from the neutral atom. So in the case of -3, it has 10 electrons. In the case here, it actually has 7 electrons. So this guy would actually have 7 electrons. So the difference there, again, between the neutral and the guy with the charge is it gained basically 3 electrons. And that's basically what happens when we are dealing with an anion. The reason it is negatively charged is because it gained electrons. And what that means is in that situation, that particular atom, if you will, has more electrons than protons. So it has a greater negative charge than a positive charge because of that. And it actually will gain those electrons. The opposite is sort of true here if we had, say, iron, for example, and we did iron with a +3 charge and our 56 and our 26. So this is, again, pretty close to this guy here. The only difference is we have a +3 charge. In this case, the atomic number is going to be 26 still, which means the number of protons is 26. So we've got 26 positives. The number of electrons in this case will actually be 23 electrons. 26 positives plus 23 negative charges from our electrons leaves us a net of a +3 charge, which in this case is where that +3 charge comes from. And again, we see in this particular case, when we become positively charged, in the neutral guy, it had 26 electrons. In the guy with a positive charge, it had 23 electrons. And the difference is that it actually lost 3 electrons in this particular case. And that's how we get things that become positively charged, is that they lose electrons and become cations. In the case where they lose electrons, they then have more protons than electrons. So more positive guys than negative guys. And that's why we see them ending up with a positive charge. Question on what happens when we do have a charge here. Now, as we talked about, the only thing that changes in all these guys are the electrons. As we talked about before, we don't change the protons because if I decided, oh, I'm just going to change my iron to 23 protons or something like that, or 29 protons or something like that. If I changed it to 29 protons, I would no longer be talking about iron. I'd be talking about copper. So remember, you can't change the proton, because if you do, you change the element you're dealing with. It has to be just the electrons when something gains a charge. So something becomes positively charged, they lose electrons. Something becomes negatively charged, they will gain electrons. So why don't you try one here? Why don't you do, let's do nickel with, let's do nickel with a +4 charge with, we'll do 20 neutrons. And why don't we do like bromine with a -1 charge with, we'll do 35 neutrons. All right, so for each of these, why don't you write the correct symbols with the mass number, atomic number, and also how many protons and electrons would each of these have. So take a minute or two. You might need to look at a periodic table. Hope we got one laying around. Okay, so let's take a look at it and see. We'll start with the nickel. So if we go to the periodic table, which obviously would be very helpful, I'm imagining. If you went to the periodic table and you found nickel, you would see 28 and nickel. Maybe like that, maybe better written. There we go. And again, obviously, the important piece of information, remember, is the top number, bottom number. Leave it alone. Don't play with it. Top number there is 28, which tells us that is the atomic number for our nickel, which means we can kind of put that into our symbol if we like. And that should go again here on the bottom number. Because the atomic number there is 28, that tells us that we have 28 protons. And adding those together gives us a 48 there for our, that's what I did there, 20. That gives us a 48 for our mass number, which would go up on top and it would have a +4 charge. Now, in this particular case, with a +4 charge, what that would mean is, again, we have 28 protons, which are positively charged. In this case, it would have only 24 electrons, which are negatively charged. That is going to give us our +4 charge. And again, what that essentially means is that it has now lost 4 electrons from the neutral nickel. Neutral nickel would have 28 electrons to match. And in this case, we lost 4 electrons, which means we have more protons than electrons, and why we ended up with a +4 charge. Question on that one there. Looking at Br minus, again, we can go to sort of the periodic table there and look at Br. Br looks like it is 35 there. So that 35 is going to give us our mass number, atomic number, I'm sorry, which should go on the bottom. That's also going to tell us that bromine here has 35 protons. That means if we add them together with, what did I say, there are 35 neutrons as well, gives me 0,670 in terms of its mass number. And it obviously has a -1 charge. So same sort of thought process here. We have 35 protons, which are positively charged. In this case, we are -1, which means we actually end up with 36 electrons, gives us a -1 overall charge that we see there. Any questions on how to figure out protons, electrons, neutrons, or things with charges? Now, you probably can pick it up, but again, just to point it out to you, when we look at something that has a charge, a couple of things tells us what's going on. When we see a minus, it automatically should tell you that it has gained electrons from the neutral guy. And the 3 is how many electrons that it gained. And again, as we talked about, it went from 7 electrons in the neutral to 10 electrons here in our -3 charge. So 7 plus 3 is 10. Same thing here. The plus tells us it actually lost electrons. The number tells us how many it lost, which is 3. And that's what we saw. Iron had 26 electrons originally in the neutral, ends up losing 3 electrons, and ends up at 23 there with our positive charge. Any questions on any of that there? Okay. All right, so to sort of finish up this chapter here, we're going to talk a little bit about energy. And as I mentioned a number of times, I think yesterday as well, we really don't talk about energy very much in this class at all. I believe, if I'm not mistaken, it's chapter, I want to say it's chapter 6, maybe. Could be wrong, somewhere in that ballpark. But that's sort of the energy chapter, and they've taken it sort of out of our class and put it into 200B. But we do talk a little bit about energy along the way, as obviously, as I mentioned yesterday, the book sort of assumes that you've done that chapter probably. So we will see a little bit of energy, but we don't like really delve deep into energy and energy calculations and stuff like that. Again, you'll get that in sort of 200B. But let's just talk a little about some energy that we will see here. And energy in terms of the ability basically to do work or to produce heat. Work is basically force acting over a distance. Heat is basically the flow of energy from one object to the next. Typically, when we have two objects that are at different temperatures and they're sort of in an insulated sort of container, heat does flow from the hot to cold. So the guy that's hotter would kind of come down in temperature. The one that's colder would kind of come up in temperature. And again, if they were sort of in an insulated sort of container, they would sort of meet somewhere there in the middle in terms of their temperature. Now, when we talk about the law of conservation of energy, as we talked about before, in terms of that law, energy is neither created nor destroyed, but it can be sort of transformed from one form to the next. There's sort of a total constant energy that's there in the universe. And when we usually talk about sort of energy and thermodynamics, which is what this is about, and you'll talk about it again in 200B, but there's usually two things. There's, when we talk about two things, there's a system, and basically everything else is the surroundings. So when we talk about something like energy, for example, the reason we sort of say there's a conservation of energy and we don't create nor destroy it is, if we had a system, which could be like a test tube, a reaction happening in a beaker, whatever it may be, if this guy gives off, say, 20 kilojoules of energy, the surroundings would then gain basically 20 kilojoules of energy. So there's almost this sort of perfect exchange, if you will, not really perfect, but a perfect exchange of energy that occurs. If somebody loses a certain amount of energy, there's something else that's going to sort of gain that amount of energy. So again, you get this sort of constant amount of energy that's sort of happening in a process when we talk about it. Now, there are different types of energy. Energy, again, has the capacity to do some type of work. There's radiant energy. There's thermal energy. Radiant energy comes from the sun. Thermal energy associated with the random motion of atoms and molecules. And, when we talk about energy, and we talked about it a little bit, I think, the other day as well, when we talk about sort of the energy of a reaction or the heat of a reaction and those type of things, a couple of symbols that we sometimes will see. We oftentimes will use Q for heat. And again, you may be familiar with Q using that specific heat equation. Q is equal to ms delta T. And that's the equation that you typically use, as we talked about a little bit yesterday, to figure out how much heat or energy occurs as you change the temperature of a substance in the same phase. Very often, though, in sort of general chemistry, we oftentimes will look more at what is referred to as delta H, which I think we also touched upon yesterday, which is the enthalpy. And that's sort of the heat of a reaction. In a constant pressure situations, the delta H is equal to Q in sort of a constant pressure situation. So that's why we oftentimes will sort of default to sort of delta H in a lot of cases. And delta H basically tells you a couple important things about a reaction. And we also talked about it yesterday, but again, a reminder that, if we do have a reaction which is considered to be sort of exothermic, or a process that's considered to be exothermic, that means that heat and energy is released. And the way that is basically reflected in terms of numbers is Q would be a negative value and delta H would also be a negative value. So when we talk about sort of energy values and we end up with a negative sign, that usually indicates that that's an exothermic reaction and heat and energy is being given off. And that's opposite of the other type of sort of process that we oftentimes come across, which is our endothermic process. And as we talked about, I think yesterday as well, that's when heat and energy is absorbed. And that again gives us a more positive value when we calculate things like like Q or H. And that tells us that it is endothermic, sort of things are being absorbed. Now, there's also chemical energy, and that's energy stored within the bonds. So when we think about making and breaking bonds, there's sort of energy that's sort of required to do those things. If we wanted to break a bond, if you have a bond and you want to break a bond, you actually need to put energy in to do that. When you put energy in, everybody in that bond gains enough energy and they wiggle away from each other. It doesn't exactly happen like that. And that's actually an endothermic process. Heat and energy needs to be put in to basically to break bonds. And the opposite is true. If we want to make bonds, we got everybody kind of by themselves wiggling around. when they lose energy in an exothermic process, they kind of slow down and they're able to sort of come together and make a bond. So bond making is actually an exothermic process, and a bond breaking is actually an endothermic process. And when we actually talk about the bonding chapter, we will get into probably the only place we do like an energy sort of delta H calculation. We will do those type of calculations there. And you can kind of figure out, is that process making and breaking of bonds in a chemical reaction, does that reaction exothermic or endothermic overall based on how many bonds were made and how many bonds were broken. Yeah, you could use it if your question is on this equation here, Q is equal to ms delta T. Sometimes people will use some different symbols for S. The S here is specific heat capacity. Is S. Some books even use SH. Some books will use C as well. So it's all very similar type of guys. Yeah. Sometimes they'll use some different symbols for specific heat capacity. Other questions? So when we talk about other types of energy, there's nuclear energy, which we touched upon, I think, as well, yesterday as well. That's the energy that's stored within the neutrons and protons. And in 200B, when you talk about nuclear chemistry, one of the things is what is referred to as binding energy, and that's the energy required to kind of form a nucleus with protons and neutrons, and there's sort of a net change of energy that occurs in that process as a result of the different masses that are there. Potential energy is that classic one, right? The big giant boulder right up on the hill, about ready to fall on somebody's head. That's sort of your energy due to your sort of location, if you will, or position. And then obviously if it tips over the hill, the boulder, it will start coming down. And obviously that can be converted into kinetic energy, which is another type of energy. And that's the energy due to basically the motion. And if it ran over that person, the big boulder, as it came down the hill, it would stop at a new potential energy and stuff like that. So, you know, that classic, like we have the giant boulder on top of the hill, has a certain potential energy. And then obviously if it tipped over, then that would be converted into kinetic energy. It would come to rest over here at some point and have a new potential energy. And you may be wondering, well, what happened to all that energy? Well, that energy goes transferred as it's moving down. And as it hits here, it's going to transfer some of that energy, obviously, to the ground and so forth. And again, that sort of exchange of energy that occurs. You can calculate the kinetic energy by taking half the mass times the velocity squared. We really don't do that much of calculations. Very common units of energy, though, that we do come across here in chemistry, especially general chemistry, are joules and kilojoules are very common units of energy. Calories, that's lowercase calories, and kilocalories are also very common units of energy. Joules and kilojoules we see a lot. And as we see on the bottom here, there is a relationship in terms of a joule and some other units that we will actually see in our class here. And then maybe the next chapter, I think we will see it. A joule is equal to a kilogram meter squared second squared. So that relationship we actually do see in this class in a couple of places. And it's why we have to do certain calculations a certain way, as we'll talk about when we get there. But that's a good relationship to remember, that a joule is equal to a kilogram meter squared over second squared. And when I talked about sort of lowercase c here, that is because, as you may be familiar with, there is a capital calories exaggerated by the big C there. And that is more of a nutritional calorie. One of the capital C's is equal to 1,000 of the little c's. And that is equal to 1 kilocalorie. And that's basically a nutritional calorie that you do commonly see as well. And again, here are some of those units of energy, which are important. A joule is also a Newton meter. Yeah, very rarely, I say, in chemistry, you come across a Newton meter, but we do come across this relationship that we just talked about a good number of places. By the way, a calorie, which is a little c, the definition of it is really the amount of energy that's required to raise 1 gram of water by 1 degree Celsius. It's almost the same definition or similar definition of why, if you remember, kind of specific heat capacity. That is the amount of energy required to raise 1 gram of a substance by 1 degree Celsius. And that's why when you think about the specific heat of water, for example, 4.184 joules per gram per degree Celsius, are 1 calorie per gram per degree Celsius. The amount of energy required to raise 1 gram of a substance by 1 degree Celsius is why it has all those units. And the same thing here, calorie per gram per degree Celsius, energy required to raise 1 gram of a substance by 1 degree Celsius. That's why specific heat capacity, when you did use that equation I put up a second ago, that's why this guy has all 3 of those units, and this guy has just the 1 unit, either a joule or calorie usually. And that's why this is a common conversion in chemistry between joules and calories. 4.184 joules is a calorie in that particular case. And again, we really won't be doing specific heat type calculations, are really enthalpy calculations as well. All right, so as we talked about, again, you know, we talked about it yesterday, but just to remember, it is a major theme and a major reason why we do see certain things throughout everything that we'll talk about this semester, is that basically opposites attract, right? The attraction between oppositely charged particles. That again is what is sometimes referred to as electrostatic attraction. And by the way, the degree of attraction between, say, these guys, it does increase with charge. So something that is +3 and -3 will show a stronger attraction than something that's like, say, +1 and -1 coming together. So actually the charge or magnitude of the charges has an effect on how strong of the association that we do see between those guys. Any questions on that there? That actually does wrap up chapter 1. Any questions on anything that we talked about here in chapter 1 that I can answer for you? Okay, so let's give me 1 second here and let me get the next chapter. We're going to roll into chapter 2 here. Talk about here chapter 2, and in chapter 2, we're going to get into all kinds of stuff involving really electrons. So we're going to delve more into electrons. We're going to talk about waves and, you know, sort of modern atomic theory, about our quantum mechanical theory as well, a little bit in terms of waves, the nature of waves, energy associated with waves, what happens really as electrons sort of transition from one energy level to the next. We will also get into electron configuration. We'll also get into really quantum numbers and where, you know, really electron configuration comes from, why there's like s orbitals, p orbitals, why they're so, you know, why do we have, you know, 3 of one and 1 of the other and those type of things. So we're going to get into really all that here in this chapter. So a lot of look into sort of electrons. So that's different colors of fireworks, which are coming up. But grab something to write with. There we go. But, you know, really why we see sort of different colors in fireworks and some of the stuff that we're going to kind of talk about here in this chapter, it really does involve the electrons and what happens with electrons. And the basic concept of what we'll sort of be talking about in this chapter is this idea that, you know, we have maybe some energy here levels. And we have, say, an electron on a lower energy level. And for some reason, it gets excited, it gains energy, and it's able to kind of work its way up to a higher energy level. And as we'll sort of talk about sort of in this chapter is the idea that, you know, things for the most part want to be in lower states of energy. Lower states of energy are really the most important thing, is kind of the most stable sort of position for things to be in. Things that are in sort of higher energy situations really don't want to be there, really are usually in most cases not so happy to be in that higher energy level, and eventually wants to kind of work themselves back down in terms of energy to a lower state of energy. And that's what happens, you know, if you had electrons from some certain elements, this electron will eventually want to work its way sort of back down. Now, as we talked about, there is that conservation of energy, which means in order for it to come back down, it actually has to give off energy. And it may give off energy in the form of a photon of light, and that photon of light may have a specific wavelength, and that specific wavelength may correspond to the visible part of the spectrum where we actually see color, hence the different colors that we see here in our fireworks, right? So if you think about fireworks, they launch fireworks, right? They explode because there's some obviously explosives in it. That's going to provide a lot of energy. It's essentially going to excite the electrons in those elements that are in the fireworks to higher energy levels, and they're going to come back down. And as they come back down, basically in terms of energy, they're going to give off energy in the form of waves that we can see in the visible part of the spectrum. And obviously we see the different colors that occur within a, say, fireworks show and stuff like that. So we again do get different colors because of those transitions of those electrons that are happening. Why do different sort of chemicals give us different colors? It has to really do with the electrons that they possess and what energy levels those electrons are on as to what transitions that we typically would see. And that brings us to really electromagnetic radiation. And electromagnetic radiation is basically one way that energy basically travels through space. And there's three characteristics basically of a wave is basically what we're talking about here. So we could have a wave that's traveling through, and as the wave is traveling through space, it obviously has a certain amount of energy associated with it, has a specific wavelength that we'll talk about what that is in just a second, obviously a certain frequency, and is moving at a certain speed. So let's talk a little bit about that. The wavelength, which is abbreviated with a lambda symbol. I'm not really sure where that lambda symbol went, so we'll write that in. So lambda symbol is basically the distance between two peaks or troughs there in a wave. So if I draw my really bad wave here, that's that's like a surfing wave right there, I think. Let's try that again. Let's give that one more try here. All right. So I don't know. I just want to go surfing today, I suppose. All right, so we'll go with that as sort of a wave here. That's a very bad wave. All right, gosh, let's go curve that out a little bit. All right, third time's a charm, I think. Here, let's try this here. No, we'll just build it like this. There you go. All right. So the distance between two peaks there and my imperfect wave there is again our wavelength, or again, you can go from trough to trough as well. Another sort of characteristic of a wave is the frequency, which is nu there. And again, that's not a V, it's a nu. So it's a letter there in the alphabet there. And wavelengths are typically a lot of times in meters or centimeters or stuff like that. Frequency is basically reciprocal seconds. Reciprocal second and frequency, another way is commonly given is a hertz. So a reciprocal second, which could be written like that, R reciprocal second, R a hertz. They're all basically the same thing. They're all equal to each other. They're all basically what frequency is commonly given to us. And the speed of light, which is C here, is 2.9979. I personally go with the 3 times 10 to the 8 meters per second in terms of the speed of light. Again, you can use either number if you like. I think your lab manual may round this to like 8 or something like that. But personally, I just roll with the 3 times 10 to the 8 meters per second. And the frequency, again, is basically, you know, how many times sort of the wave passes a particular point, you know, per second. And this allows us to sort of calculate certain things because the speed of light is equal to the wavelength times the frequency. And if we just think about units, meters for our wavelength, reciprocal seconds for our frequency, and that is how we get with meters per second in terms of the units there for our speed of light. That's sort of an important equation, which I think we'll see here, but you could also use this to rearrange and solve for the wavelength. The wavelength would equal the speed of light divided by the frequency. And you could also obviously solve for the frequency, which would be similar calculation, speed of light divided by the wavelength. So again, that's sort of 3 ways of that equation that can be used and rearranged to solve for either the frequency or the wavelength. So if you have those given to you, you could definitely calculate them. And again, in terms of units, especially when you're using these formulas here, we do want to make sure meters for our wavelength, and again, our frequency usually are reciprocal seconds. Any questions on that there? So those obviously equations you do need to know, or at least the top one, and how to properly rearrange it obviously would be good as well. And there's that right there. All right, so why don't you try one here, see what you come up with. We're looking for the wavelength of red light with a frequency of 4.62 times 10 to the 14 reciprocal seconds. And let's do it in nanometers. Give the wavelength in nanometers. And in case you're not sure, nano is 10 to the minus 9. All right, so take a moment or two to see what you come up with. Okay, so let's take a look. We want to calculate the wavelength. We're given the frequency, so obviously the equation that we just saw, the speed of light is equal to the wavelength times the frequency. In this case, we're going for the wavelength, so we want to rearrange it. The wavelength is equal to c divided by the frequency. Remember that c is a constant, which is the speed of light, 3 times 10 to the 8 meters per second. So we pretty much can plug it in there. We're going to take 3 times 10 to the 8 meters per second divided by our frequency, which was given to us, 4.62 times 10 to the 14, it looks like, reciprocal seconds. Now, also very important, right, that you know how to properly use your calculator here. So let's just take a moment and talk about numbers in scientific notation here. When we have a number in scientific notation and you want to punch it into your calculator, you should be using your exponent button. If you're not sure what your exponent button is, there's usually 3 options these days. You usually have a button that is an EE button. You have a button that is an EXP button. And some of the newer ones will actually have a button that is times 10 to the N. Now, if you have both of these buttons, that's good. When you would put in a number, for example, like we'll do our speed of light, you would type in 3, you then would hit the exponent button, that would usually put up a 3 and an E, or maybe on your calculator, a 3 and a couple of zeros pop to the top or something like that. When you hit that exponent button, that represents the times 10 part of the number, which means you should not be hitting the multiplication button. You should not be doing like shift log or anything like that, because that is incorrect. And then we would then put 8, because it's times 10 to the 8, and that would put an 8 there. That would turn that into an 8. Obviously, if you had a negative exponent, you would again use your negative button, not your subtract button. Yeah. If you have this one, not a big deal. The only thing is you do need to be careful when you use that as your exponent button. You do need to put parentheses around the entire number, every number that you use in scientific notation. So what you would do if you had that button is you would open a parentheses, you then would hit 3, and then you would hit your exponent button. And in your case, it most likely will do like a pop-up zeros, maybe a times 10. And then you would hit 8. And then oddly, you would then need to probably hit your little circle guy, this guy, to bring your parentheses or your cursor back down and close the parentheses, because you'll be up on top at that point. And that would be the way that you would put it in there. So you want to make sure, definitely anything in scientific notation, that you are using the correct button. Otherwise, you will find yourself off in terms of the answer. And usually what you'll see is the front part of the number will look okay in terms of your answer, but the back part with the exponent will look incorrect. And that's usually a good sign that you are definitely punching it in incorrectly into your calculator. So you should never be hitting the multiplication button when you're doing scientific notation. You should never be using the shift and log button or anything like that. That is the proper way to doing it. So in my case here, I would go 3 exponent button 8 divided by 4.62 exponent button 14. And what I would end up with is a bunch of zeros, but I will end up with, if I put it back into scientific notation, we'll call it 6.49 times 10 to the minus 7. The units here would be meters in this case, as the seconds would cancel each other out. First off, any questions on that there? That is meters, but we want nanometers, so we do need to do a conversion. And also another very common thing that people screw up on is this right here. When you see something like that, like nano is 10 to the minus 9, kilo is 10 to the 3, whatever it may be, what that means is that's how much there is in the base unit to one of the prefix units. So what I mean by that is, what that number means is in 1 nanometer, one of the prefix units, there would be 10 to the minus 9 meters, one of the 10 to the minus 9 of the base unit. The base unit is meters here. So 1 nanometer is 10 to the minus 9 meters. It is not 10 to the minus 9 nanometers in 1 meter. So that's a very common thing people screw up on as well. So you got to be careful on that. So we would take 6.49 times 10 to the minus 7 meters. We would actually be dividing by the 10 to the minus 9 meters is a nanometer. Units cancel, doing some dimensional analysis here. Dividing by basically 1 times 10 to the minus 9 gives us 649 nanometers, which puts us in that visible part of the spectrum. Question on that calculation there. So again, those are two very common things that people, well, screw up on. As is punching it in incorrectly in their calculator in terms of scientific notation. And this is a very common one as well, this sort of conversion. Any questions on either of those? Okay, so why don't you maybe try another one here. So calculate the wavelength, and we'll do this one we'll do it in meters. So calculated in meters. And of a red light with a frequency of, that was the one we just did there, sorry. Like, it sounds very familiar. Let's try this one here. Calculate the wavelength of a radio signal with a frequency of 100.7 megahertz, and this one we'll do in meters. And mega is 10 to the 6. It is 10 to the 6 there is mega. All right, so take a couple moments and let's calculate. Okay, so let's take a look. And again, here we're looking for the wavelength. So that's going to take us to our equation here. I'm going to solve for wavelength again, which is going to be our C over our frequency. And again, C being our speed of light, which is 3 times 10 to the 8 meters per second. Here we have megahertz, and remember that it may not sound like a frequency to you, but remember that a hertz is the same as a reciprocal second. So this is basically just a version of hertz, which is a version of reciprocal seconds, but it is mega. So we do need to do conversion. So again, that all the units cancel out correctly. So we do want to convert the megahertz into hertz. So if we did that, we would have 100.7 megahertz. Again, mega is 10 to the 6. So what that means is in one of the prefix units, so 1 megahertz, would equal 10 to the 6 hertz. The base unit here is a hertz. So 10 to the 6 hertz is 1 megahertz. And again, that is how you want to use that conversion correctly. And that would give us 1 megahertz on the bottom and 10 to the 6 hertz on top. We're multiplying across the top and dividing by the bottom. So we're basically taking 100.7 times 10 to the 6, which is going to give us, and by the way, that is 1 times 10 to the 6 if you need to punch it in that way on your calculator, 1.007 times 10 to the 8 hertz. And again, that is the same as 1.007 times 10 to the 8 reciprocal seconds. Any questions on that conversion there? Now that we sort of have our frequencies in the right units, and the reason we need it sort of in reciprocal seconds is because the speed of light's in seconds, and that way everything cancels out correctly. We can punch that in. Wavelength is going to be our 3 times 10 to the 8 meters per second divided by our 1.007 times 10 to the 8 reciprocal seconds. And that gives us looks like 2.98 meters. 98 meters as our wavelength. And that does make sense for a radio wave. It has a longer wavelength than visible light, and that does make sense there. Any questions on that? Now, by the way, when we're talking about scientific notation, just a reminder that it should be n times 10 to the n. This should be a number between 1 and 10. This obviously is a whole number. That's either positive or negative, depending on which way you go. And that's why, you know, you would write it like this. You should never have, you know, scientific notation written like, say, 30 times 10 to the 7 or something like that, or 10.07 times 10 to the, I guess it would be 7 or something, you know, or 0.107 times 10 to the whatever. So those are all incorrectly written. The front number has to be a number between 1 and 10 for it to be properly written. Any questions on any of that there? Okay. So I know we're sort of at the end of lecture here, but I do want to talk about 2 more slides, which will be helpful for our lab today. So we're just going to go just a little bit longer here in lecture, and then we'll take a break, and then we'll do lab a little. We'll start lab a little bit later here, just to finish these next 2 slides, since it sort of, I think, will relate to what we're going to be doing in lab today. So let's take a look at these next guys here. Again, there we go. So the nature of waves, there is a relation. Let's come back. There is a relationship between waves, wavelength, and energy. And what we see is when we look at, say, these are 3 waves of color. Basically, we have red, we have green, and I guess bluish there on the bottom. And when we look at the wavelengths of each of these, we do see the red here has the largest wavelength. The green here has the next, and the bluish one here has the smallest in terms of wavelength. And when we talk about the relationship between wavelength and energy, when we have a wavelength that is shorter, it typically will have a much higher energy, and also a shorter frequency as well, or higher frequency, I guess is a better way to say that, higher frequency. When we have a wavelength that is longer, we have usually a lower energy wave. So if you just think about a wavelength where, you know, the wavelength is pretty spread out like this, it's not moving as fast as like the guy on the bottom where it's just kind of going, repeating very quickly, very badly. I'm not doing well in wave drawing today. Very short waves here, and a much higher frequency, and it has a higher frequency and a higher energy. That's what I was trying to say, a higher frequency. And this guy would have a lower frequency and a lower energy. So when we look at these guys in terms of these different colors, which would be part of the visible part of the spectrum, the visible part of the spectrum is where we see color, like our Roy G. Biv, right? Red, orange, yellow, green, blue, indigo, violet. What we see here in terms of red, we would expect it to have the lowest in energy. It has a longer wavelength, a lower frequency, and a lower energy, and down here would be a higher energy, as it has a shorter wavelength, a higher frequency, and a higher amount of energy associated with it. Any questions on that there? And that does tie into the electromagnetic spectrum. And electromagnetic spectrum is basically some different areas where, you know, depending in relationships to sort of what we're talking about here, where we see the wavelength of the wave that's coming off sort of falls. So when we look at this, this is in meters, 10 to the 4 on this side, 10 to the minus 12 on this side. That is a much smaller wavelength. This is a much larger wavelength on this side. And that means that on the left-hand side, we would expect this to be higher in energy. And on this side, it would be lower in energy. So sort of on the lower end of the spectrum on the right-hand side there in this picture, we have things like radio waves, like we just calculated there. Radio waves like 298 meters, or 2.98 meters, you know, puts us in this range. When we kind of go to the left, we then pick up some stuff that has a little bit more energy. So we hit things like microwaves, which has enough energy to kind of spin water molecules a lot faster, cooks your pizza very, very quick. Going next door, we pick up more energy in the infrared. That's where we feel heat and the sort of energy sort of coming off in the infrared spectrum. Then we have our visible part of the spectrum next. And the visible part of the spectrum is obviously, you can see the colors. That's where we see colors. And obviously this is like we were talking about our kind of red, orange, yellow, green, blue, and violet sort of at the very extreme there. And these guys are typically given in the visible part of the spectrum a lot of times in units of nanometers. So when we get kind of to the visible part of the spectrum, we often give it off in nanometers, like the example we just did there where we hit whatever it was, 649 nanometers, which kind of puts you over in this range. And again, if a wave comes off with a wavelength within this spectrum, you will see color basically occur. If it comes outside of the spectrum, we won't see color, obviously. It'll be when one of these sort of guys. Next, we are going into ultraviolet. We gain some more energy. We're obviously increasing energy now going to the left. Ultraviolet, like why we put sunblock on right when we go outside so we don't get too burnt and stuff like that. Obviously, high energy and stuff like that. Obviously, X-rays, high in energy as well. X-rays, why they put on a lead vest for you when they give you an X-ray, why they leave the room usually. When they take the X-ray, is high in energy. You obviously don't want to be exposed to that. And gamma rays, as we talked about, when we're talking about sort of Rutherford's experiment, is basically just pure energy. So there's radioactive waves, pretty much pure energy, kind of as highest in energy as you can go. So when we look at this electromagnetic spectrum, you do need to know the electromagnetic spectrum. You need to know it in the sense of which one would be, say, higher in energy, which one would be lower in frequency, smaller wavelength, longer wavelength. You won't be asked, a specific like what is the wavelength where microwaves come off, but you do need to know sort of the order and be able to put them in order based on sort of wavelength, energy, that type of thing, but no specifics in terms of the numbers. You also need to know in terms of the visible part of the spectrum there, what color is higher in energy, which color is lower in energy. And again, just in case you're not sure, we see red on this side. Red is lower in energy because it has a longer wavelength. Then when we come over to sort of the violet side, that is higher in energy in terms of a color because it has a shorter wavelength. So you do need to know the order. Again, you don't have to know the specific numbers where like red is between or like yellows between or stuff like that. But you do need to be able to put it in order based on like if you're asked, hey, put these guys in order from longest wavelength to shortest wavelength or lowest energy to highest energy. You need to be able to do it that way. Any questions on that there? Okay, so I think that's good. Here we will stop with lecture.